Let's now switch gears and cover reactions of alcohols. One of the things we can do with alcohols is convert them into alkyl halides. Now, generally, alcohols or the OH on an alcohol is considered a poor leaving group. So in order to do a substitution reaction and replace it with a halogen, we have to first turn the alcohol into a better leaving group. One of the ways we can do this is by adding an acid that also contains a nucleophilic halogen. So for example, HCl, HBr, or HI. These work well or really well with tertiary alcohols through sort of an SN1 reaction. An example or general example is shown here, where this tertiary alcohol, if we add HCl or HBr, we can protonate the alcohol and turn it into a water leaving group, which would eliminate through an SN1 reaction to form a carbocation. And then in a second step, a chloride or a bromide would add to this carbocation to form the alkyl halide. Of a tertiary alcohol reacting with HCl, forming a tertiary alkyl chloride. Now, this reaction works best with tertiary alcohols, followed by secondary alcohols, followed by primary alcohols, and methyl alcohols generally do not react very well in this reaction. The reason for this is because the mechanism involved is an SN1 mechanism. Alcohols generally react with acids such as HCl and HBr through a combination of SN2 and SN1 reactions. The SN1 reaction will lead to a carbocation rearrangement in some cases, and so you may sometimes obtain a product that has the halogen in an unexpected location. Here's an example of a secondary alcohol reacting with HCl. Notice we have to heat this reaction. If it was a tertiary alcohol, typically it would react at room temperature or sometimes even lower. The product that we obtain is a tertiary alkyl halide. Notice the halogen is not in the location we would expect, which is what we see with the minor product. The reason for this is the secondary alcohol is protonated by the acid as usual. That eventually leads to the alcohol being eliminated and forming a carbocation, a secondary carbocation. Now that secondary carbocation can react with the chloride to form the expected product, which turns out to be the minor product in this example. Or the carbocation can undergo a hydride shift. So an adjacent hydrogen on the tertiary carbon next door would move over with the 2 electrons in the bond and therefore do a hydride shift. That would result in a carbocation being placed now at the tertiary carbon, which would be attacked by a chloride to form the major product. Primary alcohols generally are even slower than secondary alcohols, so we have to heat them up to react with HCl or HBr or HI. Now, typically the reaction will occur through an SN2 type reaction since we're involving a primary alcohol. Here's an example of a primary alcohol with HBr leading to a primary alkyl bromide. A primary alcohol reacting with a HI will lead to a alkyl iodide, and a primary alcohol with HCl will lead to a primary alkyl chloride. Primary alcohols generally react with acids such as HCl, HBr, and HI through an SN2 type mechanism, since formation of a primary carbocation, which would be required for the SN1 mechanism, is unlikely to occur. A primary alcohol would first be protonated by the acid to form a protonated alcohol. This is turning an alcohol into a much better leaving group once it's protonated. In the second step, the halogen would attack the carbon where the alcohol is attached to. that would lead to an SN2 type reaction. So like any SN2 reaction, this would be a backside attack, eventually leading to a bromide being attached where the alcohol used to be. Alcohols can react with tazol chloride to form tazolates. A general example is shown here where an alcohol reacts with the sulfur and replaces the chlorine to be attached now to the sulfur and therefore form a tazolate group. Tazolates, as we have mentioned before, are equivalent to an alkyl halide, and we can do substitution reactions on them. So they have a lot of uses. Here's an example with a secondary alcohol. Notice the alcohol is facing back, and if we reacted with tazol chloride, we would turn that alcohol into a tazolate. Notice the stereochemistry does not change since it is the alcohol that is attacking the sulfur, and therefore there's no need to invert the stereochemistry at this carbon. Once you have a tazolate, you can do all sorts of reactions on them, treat them as an electrophile, so you can add various nucleophiles such as sodium methoxide to attack the carbon through an SN2 reaction and replace the tazolate, and also change the stereochemistry in the process. So the tazolate was facing back, the nucleophile will now be facing forward. Note that if we use a strongly basic nucleophile, such as one of the koxides, such as sodium methoxide, these can also be bases. They're generally will also act as bases. So not only are we going to get SN2 products from this particular reaction, we're also going to get a lot of the E2 product as well. Here's another example of a primary alcohol being turned into a tazolate, and then that tazolate can be replaced by a hydroxide group and turn it back into an alcohol. A tazolate can be formed from a secondary alcohol and then use a sulfur nucleophile to replace the tazolate and therefore attach a sulfur. If the stereochemistry of the tazolate is facing up, then the nucleophile will be facing down. Chloride and phosphorus tribromide can be used to convert alcohols into corresponding alkyl halides. This works well for primary and secondary alcohols. So as an example, if we have a secondary alcohol and we add thionyl chloride, that would lead to forming a chloral sulfite, and then a halogen, the chloride, which is actually eliminated in this first step from the thionyl chloride, would come in and attack the carbon that is attached to the chloral sulfite and eliminate it to form an alkyl chloride. This is an SN2 reaction, so there will be an inversion of stereochemistry at the carbon where the alcohol used to be. A similar reaction would occur with PBr3 or phosphorus tribromide, where the oxygen would attach itself to the phosphorus and form a dibromo phosphite. The bromide that is eliminated in this first step from the PBr3 would then come in and attack the carbon, eliminating the leaving group, and through an SN2 reaction attach bromide. Therefore, there will be an inversion of stereochemistry, if there is any, around the carbon where the alcohol used to be. Here's a look at the mechanism for the conversion of alcohols into alkyl chlorides through thionyl chloride. The reaction starts with the alcohol attacking the sulfur of thionyl chloride and eliminating a chlorine. In a second step, the chlorine will attack the carbon that had the alcohol attached and eliminate the chloral sulfite that is attached to it. As a result, we get an inversion of stereochemistry since the second step is an SN2 reaction. Mechanism for conversions of alcohols into bromides with PBr3 also occurs through an SN2 reaction, where the alcohol first attacks the phosphorus of phosphorus tribromide, eliminates one of the halogens, and then in a second step through an SN2 reaction, the bromide attacks the carbon that has the oxygen attached and does a substitution reaction, leading to an inversion of stereochemistry. Here are a few examples of conversions of alcohols into alkyl bromides and chlorides through thionyl chloride and phosphorus tribromide. First example has a secondary alcohol being converted into an alkyl chloride with thionyl chloride. A secondary alcohol here is converted with PBr3 into the corresponding alkyl bromide. Primary alcohol will be converted with PBr3 into an alkyl bromide and into a chloride with thionyl chloride. And then this secondary alcohol is similarly converted into the corresponding chloride and bromide with thionyl chloride and PBr3. Question, we want to come up with a possible alcohol that we can use to make the following alkyl chloride. Notice it's a tertiary alkyl chloride. Since we're trying to make a tertiary alkyl chloride, the best way to do this would be by adding HCl through to a tertiary alcohol, and through an SN1 reaction, we would convert it into a tertiary chloride. Another option you might consider is thionyl chloride. Now, thionyl chloride converts alcohols into alkyl chlorides, but it does it through an SN2 reaction, so it's better to use it for primary and secondary alcohols instead. Alcohols can be converted into alkenes through a dehydration reaction, in other words, the loss of water. Now, we can do this a few ways. One of the most common ways is through an acid catalyzed dehydration, where we use sulfuric acid or phosphoric acid to convert alcohols into alkenes. If we start off with a tertiary alcohol, like this example, the reaction will lead through an E1 mechanism to a pair of alkenes. Notice the alcohol is attached to this carbon, so elimination would occur of either this hydrogen or that hydrogen, leading to a double bond going towards where the alcohol used to be. That would lead to the product shown here on the right, which happens to be the minor product. If we remove a hydrogen from the CH2 on the right and then form a double bond here, we would lead or make the decisive product. Since dehydrations or eliminations in generally lead to the more substituted product, also called decisive product, this is what we would expect to get. Acid catalyzed dehydration occurs by the alcohol first attacking the hydrogen on either sulfuric acid, phosphoric acid, or the hydronium ion, which is formed by sulfuric acid or phosphoric acid reacting with water first. The protonation of the alcohol leads us to turning that alcohol into a better leaving group, which would be eliminated in the next step, forming a carbocation where the alcohol used to be. And then in a second step, a base such as water would remove a hydrogen from an adjacent carbon to form a double bond. Examples of acid catalyzed dehydration of alcohols. This tertiary alcohol is converted into the decisive product. So notice there's a few options for drawing the double bond. It can occur to the methyl groups. That would be the anti-decisive alkene. The major product should be the decisive product, which would be a double bond going in this direction because the double bond would be more substituted. In the second example, we have a secondary alcohol that would be turned into a double bond as shown here. Given that this alcohol is symmetrical, this is the only possible product. In this last example, we have again a tertiary alcohol. Adding acid and heating it up will lead to the dehydration of that alcohol and forming the more substituted double bond, which would be in this direction, Or if you want, you can draw it in this direction, which would be exactly the same product based on the symmetry of the molecule. The minor product would be having a double bond towards the methyl group, which is observed in a smaller percentage. Notice that acid catalyzed dehydration is the reverse of a reaction we covered earlier, which is the acid catalyzed hydration of alkenes into alcohols. By heating the reaction and usually eliminating the water that is produced as a byproduct from this reaction, we can push this reaction forward towards the alkene. It can be oxidized into various functional groups, such as aldehydes, ketones, or carboxylic acids with different oxidizing agents. Oxidation in general in organic chemistry is the loss of bonds to less electronegative atoms such as hydrogen, or the addition of bonds to more electronegative atoms such as oxygen. As an example, a primary alcohol can be oxidized into an aldehyde. We consider this an oxidation since the carbon of the alcohol is losing bonds to hydrogens and is gaining bonds to the oxygen through this carbonyl. Aldehydes are often oxidized further into carboxylic acids. This is again considered an oxidation because we're losing a bond to a hydrogen and gaining a bond to another oxygen. So it is actually the carbon of the carbonyl that is being oxidized in both examples. Secondary alcohols are generally oxidized to ketones. Tertiary alcohols, however, are generally not oxidized unless we use very harsh conditions. The reason why they don't like to be oxidized is we do not have a hydrogen to lose, and therefore it makes it difficult to add a bond to another oxygen. Oxidizing agents in chemistry is chromic acid. Chromic acid is sometimes referred to as Jones reagent. It is something that can be made from either sodium dichromate or chromium trioxide by adding water and sulfuric acid. Chromic acid can be used to oxidize secondary alcohols into ketones. Now, note that in this reaction, generally the chromium reagent, sodium dichromate, is a red-orange color to begin with. And then once the reaction has occurred, the byproduct, the chromium, which is reduced since the carbons of the alcohol are being oxidized, the chromium will turn into a green color. Here's a look at the mechanism in a very simplistic form where the alcohol will attack chromium trioxide, the chromium in particular. It will lead to breaking this bond here. And then in a second step, a base will remove the hydrogen from the alcohol. And then a second equivalent of base will remove a hydrogen from the carbon that is attached directly to what used to be the alcohol oxygen. And in the process, we eliminate the chromium reagent. As a result, we form a double bond between the carbon and oxygen and are oxidizing the carbon of the carbonyl. The chromium, on the other hand, is being reduced. With chromic acid, primary alcohols are generally oxidized to carboxylic acids. This reaction occurs first by turning an alcohol, a primary alcohol, into an aldehyde, and then that aldehyde will react with sulfuric acid and water, which are two of the reagents that are used as part of chromic acid. And then they will turn this aldehyde into a hydrate. So the reaction occurs by the oxygen of the aldehyde first being protonated, water adding to the carbonyl carbon to form this intermediate, and then the conjugate base of sulfuric acid removes this hydrogen from the carbonyl oxygen, from the oxygen of the water that's just added here, and that leads us to the hydrate. A hydrate will then be oxidized by chromic acid once again. So one of the two alcohols that you see here can be oxidized into a carbonyl through a similar mechanism of just a general oxidation with chromic acid. There's another reagent, an oxidizing reagent called pyridinium chlorochromate, or PCC, which is a selective oxidant. It is a reagent that is complementary to chromic acid, as you'll see in a moment. So the reagent PCC is formed by taking chromium trioxide, adding ACl and pyridine to make the reagent. Unlike chromic acid, PCC is organic soluble. Chromic acid is generally used in water solutions. And PCC has one distinctive characteristic as well, that it will convert primary alcohols into aldehydes. The reason for this is PCC does not have water as part of the reaction, and so the aldehyde that is formed after oxidation of the primary alcohol is not converted into a hydrate, and therefore that hydrate is not oxidized further into a carboxylic acid. You might recall chromium trioxide or sodium dichromate, which lead to eventually chromic acid, will be used to turn primary alcohols into carboxylic acids, and they do that through the fact that they are used in a water solution, which turns the aldehyde into a hydrate and then eventually into a carboxylic acid. Well, the primary use of PCC is to oxidize primary alcohols into aldehydes. It can also be used to turn secondary alcohols into the corresponding ketone, as shown by this example with testosterone. This is a test that is administered by police to detect the amount of alcohol in somebody's blood or in their breath. So this test relies on a reaction we covered recently, where chromic acid will convert alcohols into carboxylic acids. So as an example, ethanol, which is found in alcoholic beverages, would be converted by chromic acid into acetic acid. Notice that chromic acid, as I mentioned before, is an orange color, and once the oxidation occurs of ethanol, we obtain a reduced version of chromium, which has a green color. So the breathalyzer test relies on detecting the amount of this green color and therefore determining the amount of ethanol in somebody's breath, and therefore indirectly detecting the amount of ethanol in somebody's blood. Discuss how NADH, a coenzyme commonly found in biological systems, is used as a hydrate reagent to reduce ketones and aldehydes into alcohols. The reduced form of the oxidized form of NADH is NAD+, which is actually an oxidizing agent that can reverse this reaction. So a secondary alcohol, for example, can react with NAD+ and convert it into a ketone and NADH. In this question, we're going to try to predict the product that would occur from the oxidation of these two alcohols with chromic acid. Primary alcohols such as 1-hexanol are typically converted into carboxylic acids with chromic acid. Secondary alcohols, on the other hand, are converted into ketones.